start discussing the essential aspects of semiconductor materials, we need to take a quick review of basic chemistry. Now, I know many of you are in 10th grade and are just starting your chemistry class, which is actually in part why I'm doing this. So let's just review quickly the structure of the atom. So the atom has a positive nucleus. The nucleus is positive because it is where all of the particles called protons live. And we have a negative electron cloud because electrons are negatively charged particles. There are also neutrally charged particles in the nucleus, but we're not concerned with those right now. Those are called neutrons. And an atom in general is usually what we call electrically neutral overall, because the total number of positives in the atom is equal to the total number of negatives in an atom. So for example, if we were talking about the element hydrogen, we would say there's one proton in the nucleus and there's one electron in the cloud, and as it orbits around, the total charge in the atom is 0, therefore it is what we say neutral. So when you look at this thing called the periodic table will track the name of the atom as being synonymous with the number of protons. Okay, so the atom in question for us right now is silicon, and it turns out that silicon has some pretty cool properties once it's been engineered with some cleverness, and that's what we're going to focus on. So the silicon atom is number 14 on the table, which means that it's got 14 protons in its nucleus, and it's got 14 electrons in its cloud. Well, here's where some basic chemistry comes in. The electron cloud is not just a random jumble of 14 electrons. Electrons live in what we call energy levels. And for reasons that you'll learn about in your class, the energy levels have limits on the total number of electrons that fit in them. The first energy level contains 2 electrons. The second energy level contains 8 electrons. Notice that I'm drawing them as pairs. That's not by accident. The third energy level can accommodate up to 8 electrons. But it turns out that silicon only has 14 total. Therefore, if silicon has 14 total electrons, with 2 in the first level and 8 in the second level, there's 10, so there's only 4 left to go in the outermost level. And that outermost level, called the valence layer, is very important to the chemistry of silicon because the outermost layer are where the electrons live that are going to interact with adjacent atoms. Okay? In other words, these inner electrons don't really play much role, if any, in terms of what the atom does to interact with neighbors. So, quick review. There are 4 valence electrons for silicon, 2 in the middle, 2 at the beginning, 8 in the second layer, and then 4 in the valence, because there is a total of 14 electrons to make silicon a neutral atom. So let's take a look over here at this diagram. You can see in my diagram I have what we call pure silicon. And the pure silicon is called that way because it's essentially all silicon atoms that are in a crystal with one another. And then, so let's take a look at what this cartoon. We're going to focus on this central silicon atom. So this blue thing is the nucleus, and you can see that each silicon nucleus has 4 valence electrons. Remember, we don't care about the inner electrons, it's just the valence electrons. It has 4 valence electrons to communicate with its next door neighbors. Well, you can see that this, if the central atom is doing one thing, then the atom right to the top of it is contributing one of its to the central atom. The one to the left here is contributing 1 to the central atom. The one to the bottom is contributing 1 to the central atom, and then the one to the right is contributing 1 to the central atom. And what's cool about that for the central atom is that it now has a full 8 electron complement in its outermost layer. It is now energetically stable because it has engaged in 4 sharing bonds with 4 adjacent silicon atoms. So in fact, these 4 valence electrons essentially fill up with electrons from adjacent atoms, and when we are talking about pure silicon, that will create a very specific crystalline structure. So then what goes on in other scenarios? You could, for example, bond silicon to a lot of different things. But one of the things that has been kind of the source of a lot of research and development here in Silicon Valley back in, I guess, the 1950s and 1960s was this experiment with what's called doping the silicon crystal in order to manipulate its electrical properties. So the first type of doped silicon that I'd like to introduce you to is what's often referred to as N-type silicon. So let's forget the fancy names here for a second. Remember, like we were just sorry about that. Remember we were just talking about a moment ago that silicon has 4 valence electrons. 1, 2, 3, 4. And so my central nucleus, if it were silicon, would create the crystalline structure that we just looked at. But what we're going to talk about instead is that the silicon is now going to be replaced with a single phosphorus atom. Now, phosphorus is element 15. Silicon was 14, phosphorus is 15. So rather than having 4 valence electrons, phosphorus has 5, because the phosphorus electron cloud goes 2 in the first, 8 in the second, and then 5 in the third layer to create that electrically neutral atom, 15 plus 15 minus. So that 5th electron has nothing to bond with because all of the adjacent atoms in my silicon crystal are silicon, and they only have 4 to give, right? So the idea in what we call doped silicon is that the vast majority of atoms are silicon. Once in a while in the crystal there will be an engineered phosphorus nucleus, and with that phosphorus nucleus comes an excess electron. So if you were to ask, is this whole material neutral, the answer is yes. On the other hand, that electron has nothing to bond to, so it's kind of free to move around. And that's important because that's going to be part of the conductivity, or in fact the semiconductivity of of doped silicon. So just a quick review, N-type silicon has excess negatives and therefore is called N-type because it is doped with a phosphorus atom that contributes this one unbound free to move around electron in a sea of otherwise silicon atoms. Okay, so we're almost done. We just need to discuss the final type of doping, and that is the other version, which is called P-type doping. So let me bring up my P-type drawing. So P-type silicon would be everything is silicon except very once in a while there's an atom of what we call boron. Okay, boron is has the opposite property of phosphorus in this picture. Boron is element 5. Element 5 has 5 protons, 5 electrons. The electronic structure in the energy levels would be 2 and then 3, rather than 2 and then 4 if we were to have equivalent valence structure with 4 electrons. But boron only has 3 in its valence layer. So boron, this green nucleus here, is interacting with all these adjacent silicons who are expecting 4, and we have 1, 2, 3, blank. So that boron atom is contributing what we call an electron hole because the boron doesn't provide an electron to bond with the adjacent neighbors. Now, this whole material is neutral electrically. However, that hole has nothing to bond to, and so it will also be mobile, and that will contribute to the semiconductor or the conductive properties of the material. So let me just get rid of these sketches here, and I'm just going to bring this picture back into an overview. So we've got, just to wrap this up, this is a review of what we call doping. Okay, doping is what you get when you put occasionally a phosphorus atom to create an extra electron to what we call N-type, negative silicon, or a boron atom to create an extra hole, which is what we call a positive or P-type silicon. And this is compared to what we call pure silicon. Okay, so doping is the first sort of thing to understand when you're talking about semiconductors. Junction and the depletion layer. So what we're going to do is we're going to say, let's make a sandwich out of a P-type and an N-type doped silicon. So on the right, I've got my N-typed doped silicon. Remember, N stands for negative because there are excess mobile electrons in this neutral material. And then on my P-type side, I've got an excess of holes, which are also mobile. And then when we sandwich them really closely together, something kind of neat happens. There's actually an exchange of holes going to the N-type and electrons going to the P-type, because essentially the force is set up such that the opposites attract, right? There's a motivation for these mobile particles to sort of balance out or come together with their partners on the other side of this little sandwich. Now, that action happens in a very tiny little layer that's adjacent to the surfaces. That layer is what we're going to ultimately refer to as the depletion layer. But let's dig a little bit deeper into what that means. So on the P-type side, because the electrons have migrated over to balance out the holes, the P-type side is now actually negatively charged. It was neutral, but it gained some electrons, and it's now negative. The N-type layer, negative in the very, very small region next to the surface interface. Okay, the N-type side is positive because it gained some holes, some positive charge carriers. So what we end up seeing here in this depletion layer, okay, is a permanent, or a separation of charge, whereas in the rest of the doped silicon, we've still got our excess of negatives on the N-type and our excess of holes on the P-type. So this layer is really at the core of how this junction behaves. So if you connected a battery to, let's just pretend that that's something that we could do, because I know that that's like, what even are we talking about here? But let's just pretend that we connected a battery here. If you put the positive terminal of the battery on the P-type and the negative terminal on the N-type, what you're effectively going to do is you're going to push these holes towards the depletion layer. Now, these holes will have to kind of overcome the opposition of the electric field provided by the depletion layer, okay? But they will combine with some of these negatives and actually make the depletion layer a little bit smaller. If the depletion layer gets small enough, the electrical flow can start to occur in the circuit that the battery is trying to establish. What the depletion layer ends up doing is it provides what we call a threshold voltage. And once you get over it, once you get over the initial sort of resistance, I guess, well, actually resistance is not a good word there, but the electric field due to the depletion layer initially is opposing the battery, so the battery has to overcome that. We call that the threshold voltage of the P-N junction. But once the battery overcomes that, this circuit will conduct electricity because the battery has mobile charges to push around. Now, interestingly, if we had a battery hooked up to this junction backwards, so let me just redraw. I've got going to put my N-type on the left, but connected to the positive side of the battery. And I'm going to put my P-type on the right. Sorry, I got my left and right backwards. P-type is going to go on the left. N-type is going to go on the right. The battery is positive and negative, so it's the reverse of what it was before. The situation here now is that my battery is actually working to make the depletion layer bigger, okay? Because the holes, sorry, let me grab my color. The holes are going to get pushed away from the positive terminal of the battery, and the minuses are going to get pushed away from the negative terminal of the battery. So effectively what's happening here is that the depletion zone is becoming sort of bigger or harder to overcome. In fact, if you connect the battery this way, the P-N junction will never conduct electricity. It becomes harder. Okay, we have a name for this. This is called reverse biased. Okay, reversed bias is a junction that will not conduct. Okay, now the other arrangement was what we call forward bias, and a forward bias will conduct. And then just finally, the P-N junction is at the core of what we call a diode. So a diode is sort of a key element in semiconductors and all electrical engineering. And basically, a diode is a P-N junction. The symbol for it is this. And the idea, see that nice kind of blocked vertical line? The idea is that the symbol represents the fact that current can flow through one way, but gets blocked the other way. Okay, and the reason why it gets blocked is sort of everything that we talked about before with respect to reverse bias. That's all for now. So this is an example of forward and reverse biasing. So I want to introduce you to the diode. There will be one of these puppies in your kit. Okay, this is what it looks like. And the key thing about the diode is that the gray stripe here is what indicates the N-type, part of the P-N junction. In other words, the electricity will flow through this way if you forward bias it, and if you reverse bias it, try to get the electricity to flow this way, it won't work. So what I'm going to do is demonstrate that. On the right here, I've got this ammeter hooked up, okay, and I have on my breadboard on row 40, I've got my power supply, and I go ahead and I put that in, I turn the power on, and you're going to see that the meter definitely indicates that current is flowing. Okay, so that's a forward bias diode. Now I'm going to take the diode and I'm going to reverse bias it. Okay, so just color coding wise, I've got blue as negative and green as positive, just so you know. So you can see I've got the N-type end of the diode set up to the positive side of the battery. Might not be super visible, and I'm going to turn the power supply on 3, 2, 1, go, and nothing happens. Okay, on the ammeter again, I turn the power supply on, go, and the ammeter shows no flow. Okay, so that's a reversed biased diode, and then let's just one more time here to make sure that my result is what I thought it was. This is now a forward biased diode. One more time, ammeter comes on, power supply goes off. The diode, therefore, is sort of like a one-way valve. And it turns out that the first mission of your school year is to figure out this thing called the light-emitting diode. So a light-emitting diode is one that will produce light as a byproduct of current flowing through the depletion layer. Okay, and obviously we'll spend a lot of time with that, and there's a lot of details here, but just as far as diodes are concerned, a light emitting diode is not going to show you with a stripe. Rather, the light emitting diode is going to show you with the long end being the positive side and the short end being the negative side. So if I forward bias my LED by putting it in there, I don't have a current limiting resistor in here, so that's certainly an opportunity for me to blow up my LED. But as you can see now, I turn on my power supply, the current is flowing. Okay, and then if I take my LED and it's just a diode that produces light through some physics and chemistry that we will discuss. If this is now a reversed biased diode, as you can see that I took the long end and I'm putting it on the negative side, right? Because remember, the long end should go positive, and if I turn on my current, look, nothing happens. Okay, so again, the long side goes positive, and the forward biased LED will conduct.